Section 5.8, we're going to look at something you've probably never seen before. Something brand new, hyperbolic functions. Anybody ever seen hyperbolic functions before?
Maybe. No, there's a button for it on WebAssign.
There's a button for it on WebAssign, okay.
Have you seen them in real life? Just to realize it?
Yeah, I'm looking. I don't think... yeah, I see some hyperbolic functions in this row. All right, so let's define them first. So, the hyperbolic functions. The first one is called hyperbolic sine. So it looks a lot like sine, except it's got a little h on the end of it. Hyperbolic sine. Hyperbolic sine is e to the x minus e to the minus x over 2. And then, of course, there's hyperbolic cosine. Hyperbolic cosine is e to the x plus e to the minus x over 2. And once you have hyperbolic sine and you have hyperbolic cosine, you have hyperbolic tangent. What's hyperbolic tangent? Hyperbolic sine over hyperbolic cosine. So hyperbolic tangent is hyperbolic sine over hyperbolic cosine. And you also have everything else. So for example, this one, that one's called hyperbolic cosecant, and it's defined as 1 over hyperbolic sine. Hyperbolic secant is 1 over hyperbolic cosine. And hyperbolic cotangent is 1 over hyperbolic tangent. All right, so there's at least 3 obvious questions. Number 1, you've already asked, have we seen hyperbolic functions in real life? That's one obvious question. 2 other questions you might ask. Yes. If you've seen them in real life, then yes, you will use them. That's the same question. What other questions might you ask about hyperbolic?
What do they do?
That's again, why do we see them in real life?
What do they look like?
What do the graphs look like? Okay, that's a good question. And the graphs are kind of the reason why they're called hyperbolic functions. So I thought somebody would ask, why are they called hyperbolic? Because when you think of hyperbolic, you probably think of hyperbola in math, hyperbola. So the graphs of these things kind of look like hyperbolas. And we'll see that in just a second. And then the third question is,
Is there a key in the calculator?
yes, there is a key in your calculator, I think. I know there is, I just got to remember where it is.
What's the relation to the trig?
What's the relation to the trig functions? I think that's the other obvious question. Why are they called hyperbolic sine and hyperbolic cosine? What are the relationships? All right, so let me first show you, I'm not going to draw all the graphs because they're all here in your book, so I'll cheat. Here are the graphs. So we have hyperbolic sine, hyperbolic cosine, hyperbolic tangent, and the other 3. All right, so why hyperbolic? Do you see anything that looks like hyperbolic functions there? Right, it's sine, cosine, tangent, cosecant, secant, cotangent.
So is it just rotated 90 degrees? Except for... I don't know.
This one looks a lot like the kind of hyperbolas we typically graph in a pre-calculus class. That one to me looks a lot like a hyperbolic function. Same with this one. This one looks a lot like a hyperbolic function. How about this one?
It just kind of looks like, well, to me, it
Kind of looks like a cubic, I agree.
Kind of just looks like sine tilted. Same thing with tan.
Kind of looks like sine tilted, okay, I'll agree with that. And this one kind of looks like a little piece of a sine wave, except it doesn't come back down, does it?
Well, it's not what tan inverse looks like. That
Tan inverse looks a lot like that one, yes. Tan inverse looks a lot like that one. Well, what I was thinking was sometimes when we graph rational functions, sometimes when we graph them, we end up with asymptotes like this, and you'll end up with a piece in the middle that might look like that, and then maybe you get something like this on this side, and something like that on that side. And look, that comes from a rational function, and usually in pre-calculus, when you graph hyperbolas, they come from rational functions. Now, this one is not a hyperbola, but it does come from a rational function. And to me, that looks a lot like that one. The middle piece of this function looks a lot like that one. Okay? How about this one? That one almost looks quadratic. But again, sometimes we don't do this in pre-calculus, but you can have hyperbolas that looks like that. In fact, I think you do those in pre-calculus. You can have hyperbolas that look like that. So that one really looks like a hyperbola. All right. So there's kind of the relationship, why they're called hyperbolic. They're related to, graphically, they're related to hyperbolas. Where do you see these in real life? This one's the most common one. You see it a lot in engineering, such as bridges. And where in bridges? Structural support. Okay. I can think of two examples of where you see this shape. If you have a cable and the cable is fixed on each end and it's allowed to dangle, you will get a shape that looks like this. A lot of people think it's a parabola. It's really not a parabola. It's a hyperbolic cosine. And the name of the graph, this graph has a name. This is called a catenary.
So does it, as you widen and expand on it, does it change differently then?
Yes.
Is that why it's different than a parabola?
Correct.
As you add a constant.
Yeah, parabolas tend to curve more and be more steep. It looks an awful lot like a parabola. It's hard to tell a catenary apart from a parabola just by eyeballing it. You've really got to make some measurements and formulate an equation. So when I said I think I see some in this room, I was looking at that wire that's up there, and I can see a couple places where it's taped, and it does sag just a little bit. Of course, that wire isn't completely flexible, so it's not perfect, but that wire up there would be in the shape of a catenary. And so suspension bridges, the big cables that hold suspension bridges up there in the shape of catenaries. How about if you flip it upside down? Anybody ever seen an upside down catenary? Where have you seen an upside down catenary? What's that? Every bridge in town. Probably the arches underneath the bridges supporting it are probably in the shape of catenaries. What town has the St. Louis Arch in it? I think it's St. Louis.
I was thinking, I was like, what city has the arch? And I was like, oh, it's St. Louis, isn't it?
Yes, the St. Louis Arch is in the shape of a catenary. That's probably the most famous one. And what's interesting about a catenary is they're self-supported. You need very, very little to hold it together to make it stay. Years ago, they used to have a science center over in the mall. And they had a thing where you could put a bunch of blocks together, and they had the blocks were not rectangular, they were cut. And you would put the blocks together, and they would form the shape of a catenary. And then you put them together on a piece of plywood, and then the piece of plywood was hinged, and you could lift it up, put the plywood back down, and the blocks would stand in that arch on their own. It's self-supporting. The pressure points point all in the right direction so that it won't collapse on its own. And that's how they do the arches and stuff in masonry. They build them in the shape of catenaries, and they're almost self-supporting. You need very little to hold them together.
But the arches I'm used to the concept of the keystone. How does that sort of roll?
What's that again?
I'm used to the concept of the keystone, like the centerpiece that distributes the pressure evenly across. Is that their role in catenary?
Yes, that would be part of the catenary. The keystone would usually be right up at the top.
Right.
And so if you ever go on YouTube and watch videos of how they built the St. Louis Arch, they built each side, and they had it all supported, and then they put the top piece on, bolted it in just a little bit, and the whole thing stays like that. There's very little holding that up, which is quite amazing. But yeah, the pressure coming up, pushing inward, is all captured by the keystone, and so it doesn't fall one way or the other. Very interesting structure. So, a lot of times in real life, if you see something and you think it's a parabola, it's probably not. It's probably a catenary, especially if it has anything to do with construction and supporting weight. It's probably a catenary. Where do you see parabolas in real life? Where do you see parabolas outside of a math class?
I think my math teacher told me there's a car, light bulbs, because at any time a line hits a parabola, it reflects straight back. So the bulbs in car lamps.
Correct.
Parabolas.
If you have a parabola has a point in the middle called a focus. And so if you have a light bulb here and the parabola is in the shape of a mirror, the light will go out and it will all go out in the same direction. And that's the basic idea of how a flashlight works, or how the lights in your car work. Although the lights in your car are probably not a parabola, because you don't want the lights to go straight out, you want them to spread a little bit. So they're very close to a parabola, but probably not exactly a parabola. There's a big parabola right behind you, although some of you can't look out the window, you can't see it. A satellite dish. A satellite dish works the other way. The signal comes in, hits the parabola, and all the signals bounce and go right to the focus. That's what that arm is sticking out of the middle of a satellite dish. That's where the focus is. So that's a three-dimensional parabola called a paraboloid. Next semester when you take Calc 3, you'll study paraboloids. You do multi-dimensional stuff. All right, so now, what do these hyperbolic functions have to do with trigonometry? Well, there's a lot of interesting formulas that happen to work out just right. For example, hyperbolic sine, we defined that as e to the x minus e to the minus x over 2. What happens when I take the derivative of hyperbolic sine? I get e to the x plus e to the negative x over 2. Why plus here? Because when I take the derivative of this e to the negative x, I have to use the chain rule, right? I take the derivative of the exponent, I get a negative 1. And I happen to get hyperbolic cosine. So that's just like the rules for trigonometry, isn't it? The derivative of sine is cosine. The derivative of hyperbolic sine is hyperbolic cosine. What's the derivative of hyperbolic cosine? Well, here's hyperbolic cosine, right? Take its derivative, you get e to the x minus e to the minus x over 2, which happens to be hyperbolic sine. So the rules don't work exactly, but they're close. The derivative of hyperbolic sine is hyperbolic cosine. The derivative of hyperbolic cosine is hyperbolic sine. You don't need the minus sign. It works out even better, doesn't it? Okay. And then just one more of them. How about the derivative of hyperbolic tangent? Well, that's the derivative of hyperbolic sine divided by hyperbolic cosine. And what would you need to do to take that derivative? Well, what do you think the answer is going to be? You got to use the quotient rule. And what do you think the answer is going to be? What should the derivative of hyperbolic tangent be? What's the derivative of tangent? Secant squared. So your guess as the derivative of hyperbolic tangent is hyperbolic secant squared. That would be my guess. Well, let's see. We've got to use the, what rule is that? Quotient rule. So that's the bottom. Times the derivative of the top. Minus the top. Times the derivative of the bottom. All over the bottom squared. That's hyperbolic cosine squared minus hyperbolic sine squared divided by hyperbolic cosine squared.
And I'm guessing we're not using
Which rule would you like to use?
sine squared.
For trigonometry, I know that sine squared plus cosine squared equals 1. Unfortunately, the same rule does not work for hyperbolic functions.
Split that up into cosine, cosine squared divided by cosine squared minus sine squared. Minus
Could write it as 1 minus hyperbolic tangent squared. I agree. It's even better than that, though. You were so close. For trigonometry, sine squared plus cosine squared equals 1.
It's a negative 1.
For hyperbolics, I think it turns out that cosine squared minus sine squared happens to be 1. So you were so close. You almost had the right answer. So let's see if that's true. I'm pretty sure that that's 1. And so we do get what we thought we should get. We thought we should get hyperbolic secant squared. And I'm pretty sure we do. But first I need to convince you that hyperbolic cosine squared minus hyperbolic sine squared really is the number 1. All right. So let's see if that works. Hyperbolic cosine squared minus hyperbolic sine squared. Let's see, that's e to the x plus e to the negative x all over 2 squared minus e to the x minus e to the minus x all over 2 whole thing squared. What can I do to simplify that? Well, how do I take e to the x plus e to the negative x and square it? That's a binomial, right? Two things. So I got to FOIL it out. So let's see. I'm going to get 1/4. Why 1/4? That's 2 squared, right? The bottom. That's a 2 on the bottom. And then when I square this one, I get e to the x squared plus, I multiply these two together and multiply by 2. What do I get when I multiply these two together? E to the 0, which is 1. And then I got to multiply that by 2. So that's 2 plus e to the negative x squared. So that's what I get when I square the first one. Minus, and then I do the same thing here. 1/4. I square this one, I get e to the x squared. And again, I multiply these two things together, that gives me e to the 0, which is 1, but it's going to be a minus this time, so minus 2 plus e to the minus x squared. I need myself enough room there. So some really good things happen now. What are the really good things that happen? Yeah, notice I've got a 1/4 e to the x squared, and here I've got a minus 1/4 e to the x squared. Those cancel out, correct? And then I have a 1/4 e to the negative x squared, and a minus 1/4 e to the negative x squared. Those cancel out. And then I've got a half minus negative a half. A half minus negative a half is 1. So all right, so in your book, there are a whole list of hyperbolic identities. And you should recognize that a lot of them look an awful lot like the identities for trig. This is on page 384. So this is why these are related, called hyperbolic sine, hyperbolic cosine. They're really, really similar rules. For trigonometric functions, we have sine squared plus cosine squared equals 1. For hyperbolics, it's cosine squared minus sine squared equals 1. What's the rule in trigonometry squareds and secant squareds? Well, you've got, in trigonometry, everybody remembers this one. Sine squared x plus cosine squared x equals 1. There's a rule similar to that, but it involves tangents and secants. What's the rule for tangents and secants? Anybody remember? One plus tangent squared equals secant squared. That's correct. How'd you get it, or did you just remember it? It's in the book. Oh, well, of course. I'm going to take this equation and I'm going to divide everything by cosine squared. What's sine squared divided by cosine squared? Tangent squared. What's cosine squared divided by cosine squared? 1. And what's 1 divided by cosine squared? Secant squared. So this is sometimes written as secant squared x minus tangent squared x equals 1. Okay. In the not too distant future, we're going to get to a section called trigonometric substitution, and this form of this Pythagorean identity will be very important to us. So, good one to remember. And you can see, for hyperbolics, we have almost the same identity. Tangent squared plus secant squared equals 1.
So are they all just negated?
Yeah, they're all off by just a minus sign. Okay. How about sine of x plus y? What's the formula for sine of x plus y? It looks exactly like that one. So that formula is exact. The hyperbolic formula is exactly the same as the traditional trig formula. Same with the minus one. This one's different, however.
They stay the same.
Right. Cosine of x plus y has a minus right there. But for the hyperbolics, it works out the same way. Start with a plus. Okay? They have a tangent one up there? Tangent of x plus y? No, I don't see one either.
So would tangent hyperbolic squared plus 1 equal secant hyperbolic squared?
No. Tangent hyperbolic squared minus 1 would be minus hyperbolic secant squared. So the signs are just off a little bit. Okay? So there's all those relationships between the trig identities and the hyperbolic identities. And then we already did some of these. For example, we already said the derivative of hyperbolic sine is hyperbolic cosine. The derivative of hyperbolic cosine is hyperbolic sine. You don't get a minus sign, so it's even a little bit better. Derivative of hyperbolic tangent, we already showed that one. And then the other ones. And again, they're a little bit different, not exactly the same, because the derivative of regular old secant, what's the derivative of regular old secant? Secant tangent, but the derivative of hyperbolic secant has a minus sign in front of it. Negative hyperbolic secant, hyperbolic tangent. Cosecant, yeah, it's interesting that cosecant turns out to be the same, cotangent turns out to be the same. The only two that are different are the derivative of cosine, doesn't have a minus sign, and the derivative of secant does have a minus sign. So those are the only two that are different.
Which makes sense because we're looking at changes cosine. That's why secant.
Correct. So if it makes sense that if cosine changed, secant should change because they're reciprocal functions. And then, of course, once you have derivative rules, you also have integral rules. Questions about any of those? That happens to be on page 385. So if you're thinking ahead about test number 2 and the little index card you might make, that's something that I think definitely needs to go on your index card. I don't think I would worry about this one so much. I don't usually test about these too often because those are more of a pre-calc type thing. But anytime you have rules about derivatives and rules about integrals, I think that's something you absolutely positively ought to know. And seeing as we're taking calculus, I'm probably going to test you on rules of derivatives and integrals. So that's one I would definitely put on my little formula sheet.
Was it proof for the integral of hyperbolic to hyperbolic tangent? Would that be very similar to what we did for just like inverse or just regular secant times tangent?
Well, the proof would actually be right here. Once you prove that the derivative of tangent is secant squared, then you're guaranteed that the antiderivative of secant squared is tangent. Now, a good question would be, what about the antiderivative of just tangent? That's not anywhere on here. Antiderivative of hyperbolic tangent. That's not anywhere on here. Could you come up with a formula for the integral of hyperbolic tangent? Yes, you could? All right, let's do it then.
I have a question. So, on that last problem that we did with the derivative of hyperbolic tangent, if we had continued in 9, then we got a hyperbolic cosine square or hyperbolic square. So you had 1 minus hyperbolic tangent square. That would still be secant. Secant square would be 1 minus tangent. We just manipulated tangent plus secant.
Correct. So what you said is, if I were to write this as hyperbolic cosine squared divided by hyperbolic cosine squared, that would be 1 minus hyperbolic tangent squared. And if you look here, if I were to take 1 and move that hyperbolic tangent squared over there, you would still get hyperbolic secant squared. So yes, you had the right answer, written in a different form. Absolutely. All right, so is there a formula for the integral of hyperbolic tangent? It wasn't on that table there. But can we figure one out? Yeah? Okay, how are we going to do it? Write it as sine over cosine. That sounds like a wonderful idea. Let u equal hyperbolic cosine. And then du, the derivative of hyperbolic cosine is hyperbolic sine, no minus sign, right? That was one of the things we liked about these. So this becomes the integral of 1 over u du. which is ln of u, but u was absolute value of u, but u was hyperbolic cosine plus c. So does that look very similar to the formula for integral of regular old tangent? Yep, the formula for the integral of regular old tangent was negative natural log cosine, or was natural log of secant. And the only difference was the derivative of regular old cosine gave us a minus regular old sine. Right. So yes, while those formulas are not given here in this table, and they're not ones that are going to show up very often, I don't think there's going to be any homework problems where I ask you to find the integral of hyperbolic tangent of something, but you could. And I think you could do the exact same trick and figure out a formula for integral of hyperbolic secant and hyperbolic cosecant. I think you could come up with formulas for all of them. I don't think they show up very often, though. Other questions? All right, so let's grab some homework problems. I'm on page 390. Problem number 30. Y equals x hyperbolic cosine x minus hyperbolic sine x. And the directions are find the derivative. Well, your answer would be y prime is. How do you find the derivative of x hyperbolic cosine x? Product rule. Which one do I leave alone first? Leave the x alone. And then I take the derivative. The derivative of hyperbolic cosine is hyperbolic sine plus just hyperbolic cosine, because the derivative of x is 1, minus hyperbolic cosine. So my final answer looks like x hyperbolic sine. Questions on that? F of x is arctangent of hyperbolic sine of x. I want to find f prime, correct. All right, so the first thing we need to remember is we need to remember our formula for the derivative of arctan of something. What's the formula for the derivative of arctan of something? 1 over?
U prime over U squared absolute value.
No, absolute value. So if I had just arctan x, the derivative of arctan x would be 1 over 1 plus x squared. Correct. But since I have something else, I'm going to need to use the chain rule. All right, so I'm going to have 1 over this thing squared. So that's hyperbolic sine squared of x plus 1 times the derivative of that thing. Hyperbolic cosine. Can I simplify that at all? I think I can do better than that.
Do hyperbolic tangent. What else is on
Hyperbolic cosine squared minus hyperbolic sine squared equals 1. What if I were to move that hyperbolic sine squared over to the other side? I'd have 1 plus hyperbolic sine squared equals hyperbolic cosine squared, correct? Isn't that what I have right here? 1 plus hyperbolic sine squared? So this is hyperbolic cosine divided by hyperbolic cosine squared, which is 1 over cosine, hyperbolic cosine, which is hyperbolic secant. Okay, well, this is one I didn't know then. What I just also learned is, what's the integral of hyperbolic secant? Or tangent of hyperbolic sine. Let's see. Isn't that a nice formula? Oops. I only wrote arc. I forgot the tangent part. Arctangent of hyperbolic sine plus c. I don't think I've ever seen that formula before in my life. Brand new one for me. Don't know that it's good for anything, but it's there. It's a nice new formula. True. True. All right, let's try a couple integral problems. Let's see what they have for integral problems in here. The integral. Oh, this is number 46. The integral of hyperbolic cosine square root of x divided by square root of x dx. It's hard to see. There it is. What do you do with that one? Any thoughts? It's almost always u substitution. U is square root of x, which is x to the 1/2. So du is 1/2 x to the minus 1/2 dx. Does that help? Yeah, it helps very much because this x to the negative 1/2 is the same as that square root of x on bottom, except I need a 1/2. So there's my 1/2 and there's my 2. So I get 2 integral hyperbolic cosine u du. What's the antiderivative of hyperbolic cosine? Hyperbolic sine. So this is 2 hyperbolic sine of u plus c. Final answer is 2 hyperbolic sine square root of x plus c. All right, how about one more? How about 52? The integral of hyperbolic secant cubed x times hyperbolic tangent x dx. We do not have a product rule for integrals. That's correct. That's a shame. But even if we did, I don't think I know the antiderivative of hyperbolic secant cubed. I don't think that would help even if I had a product rule. Yeah, somehow we have to manipulate these. I agree with that.
So, yeah, could you convert the tan hf, the hyperbolic function of tan to multiplied by secant hyperbolic divided by
Well, I could change this to sine over cosine. And I could change that to 1 over cosine cubed.
I think
U
U is hyperbolic secant x.
is hyperbolic secant x.
And then,
And what's du? What's the derivative of hyperbolic secant?
I think tan. Because the derivative of tan is secant, hyperbolic secant squared.
The derivative of tangent would give me secant squared. Unfortunately, I have secant cubed. You erase the 3 and put it 2. No. The whiteout. Teacher made a mistake. That's supposed to be a 2. Yeah. Try writing that on your test. See how well that goes over.
No, PS. You made a mistake here. I corrected it. You did me later.
All right, I got 2 ways to answer it. One is to do what Sam did. Convert things to sine and cosine. So this would be 1 over hyperbolic cosine cubed. And this one would be hyperbolic sine over hyperbolic cosine. So that becomes hyperbolic sine divided by hyperbolic cosine to the 4th. Now I'm ready for my u substitution. U should be hyperbolic cosine, because the derivative of hyperbolic cosine will be hyperbolic sine. It takes care of that sign on top, doesn't it? So u equals hyperbolic cosine, and du is hyperbolic sine dx. So this becomes the integral of 1 over u to the 4th. What's the antiderivative of 1 over u to the 4th? Think of this as u to the negative 4 du. What's the antiderivative of u to the negative 4? U to the negative 3, you add 1 to your power. Divide by your new power plus c. So this is hyperbolic cosine to the negative 3 over negative 3 plus c. There's answer number 1. I said I had 2 ways to do this one, correct? Hope so. Or if I don't get the same answer, I hope they only differ by a constant. But they might not be the same, but they might differ by a constant. Might be equivalent. All right, so that's kind of the brute force way to do this one. And then there's the slick trick way to do this one. I'm going to rewrite this as hyperbolic secant squared times hyperbolic secant times hyperbolic tangent. And that is what I thought somebody was doing when somebody said let u equal hyperbolic secant. Because if u is hyperbolic secant, what's the derivative of hyperbolic secant? What's the derivative of regular old secant? Secant tangent. What's the derivative of hyperbolic secant? Negative hyperbolic secant, hyperbolic tangent. So if I let hyperbolic secant, du is negative hyperbolic secant, hyperbolic tangent. Those get hard to say after a while. Hyperbolic secant, hyperbolic tangent. Whew.
So you kind of negate the integral.
So I negate the integral, and then it becomes u squared du. All right, so this is, again, kind of a preview of what's going to be coming in the near future. In the near future, we're going to do a section called Powers of Trig. And this is a typical powers of trig trick. All trick's a bad word, technique that we will learn. Look for being able to write a secant times tangent and let u be secant. That's a common technique. All right, so this becomes negative 1/3 u cubed plus c. And that's negative 1/3 hyperbolic secant cubed plus c. Did I get the same answer? Yes, because hyperbolic cosine of the -3 is another way of writing hyperbolic secant cubed. So I did get the same answer.